So in the last video, we looked at what happens when you mechanically load a tendon, and we saw there's this distinctive toe region at the beginning, then you have a linear region, and then the tendon stretches out a little bit in the plastic region, and then either breaks immediately or continues to deform and then breaks. One thing we haven't talked about yet is something interesting that happens when you actually do this experiment. So suppose you do this and you don't go up all the way and break the tendon, right? So you've got, okay, here's my stress strain curve for the tendon. But then maybe you have an idea of, well, okay, what if I stretch this tendon faster, more quickly? Something very interesting happens. The same tendon, which, say you stretched it at a moderate speed, had this stress strain curve. When you stress it quickly, it will go like this. And this is sort of supposed to be linear in here. And if you stretch it slowly, it will go like this. So this property has a name. It's called viscoelasticity. And it essentially means that the material, in this case the tendon, has a stress strain response that depends on how fast you are loading it. It has something to do with viscosity, which is a property of liquids, and it's also elastic. So if you could imagine maybe like a big bucket of paint, you may know that if you really push a brush into it really hard, it will resist more, kind of more of like an odd physics thing. But in the context of tendons, this is something that's useful to think about. So let me annotate this. Let me say like fast loading here, and then we'll say medium speed here, and then slow. And to clarify, let's maybe compare what happens at a constant level of, let's say, stress. So let's say we compute some constant level of stress, maybe 1,000 pounds divided by 1 square centimeter. We'll compare the strain of the tendon at these different levels. So for a constant stress, if that stress happens quickly, meaning you land suddenly from a jump, for example, the tendon won't stretch out as much. And that turns out to be very handy because what does damage to tendons is strain. So if you can be here versus here, that's very beneficial for not damaging your tendon. A different way of thinking about that is suppose the tendon is going to stretch out by a constant amount. If you can do that stretching at a high rate of loading, so let's say we're considering, maybe this is 4% increase in length. The other way of thinking about stress strain curves, remember, is we can think about it in terms of energy absorbed. So if you load the tendon really fast, if you stretch your Achilles tendon or your biceps tendon out to 4% increase in length and you do it really fast, you can store this much energy in the tendon. Another way of thinking about it is you can absorb that much energy. So it's like safer in a sense, right? If you're landing from a big jump. Whereas if you're loading it really slowly, you can only store this much energy. You can store less energy in the tendon. So this is beneficial from two angles. Number one, it's beneficial from an injury prevention standpoint, because you can either handle the same stress with less deformation of the tendon, or you can handle a constant deformation of the tendon with less or with more energy stored. In other words, you can absorb a bigger blow in essence. And then number two, from performance standpoint, being able to store up lots of energy like this in a tendon is super useful for running, sprinting, jumping, explosive lifting. So this viscoelastic property of tendons is very, very useful. One other thing I want to mention in this video while we're talking about these more advanced properties of stress-strain curves. I know we mentioned this when we talked about stress-strain and hysteresis for the first time, but I just want to go over again what would happen if you loaded, let's say we loaded the tendon very quickly. So we know that on the way up, its stress-strain curve would look like this. And then just as a reminder, there's this phenomenon called hysteresis, where on the way down, the stress-strain curve in reverse will look like that. And the interpretation is that the difference between these two, meaning that area, that's the amount of energy lost. So, energy lost. A perfect spring would go up and then come right back down the same way. But nothing in the real world is perfect, and so tendons you get, and again, you don't need to know this number, but I think it's about, depends on the study, but about 10% of the energy is lost. But that's a lot better than 100%. So in other words, you can retain 90% of that big amount of energy that you store up going up there. So that's viscoelasticity, an important property of tendons, and also, as we'll soon see, ligaments and cartilage. And then don't forget about hysteresis as well.